Here we're going to focus on example of the one mean t-test, but based on difference of two paired values, or mean paired difference, or the textbook puts it in a way that it's kind of weird, but I'll try to explain what it means. So suppose you're interested in the difference in prices between UCLA and Amazon books. For example, which bookstore is cheaper? Which one has higher values? Which one has lower values? Of course, in general. This is statistics, so everything is in general. So suppose you have some data on prices of books, and you have a book, Introduction to Statistics, Introduction to Philosophy, Theories in Sociology. And this is just the beginning. Maybe you have, 30 books or 50 books or 20 books, not just three, but here we can start seeing. And one of your prices is the Amazon price. And then you also have the UCLA price. And because we have these two price variables for the same unit, for the same book, we call this the paired values. Okay, it's the two different values for the same thing. Okay, so what we want to do here though is see the test to see the difference between these two values. So it almost looks like we're working with two separate variables, right? Before we were only working with one variable. Running speed is one variable. Level of mercury, one variable. Here we have two variables: Amazon price, UCLA price. They're different. You can see here they're not the same values. They're different values for the same thing. So that's what the paired means. The thing is, we don't really need to work with two separate variables. We can create a new variable here, which is the difference between the two. And of course, you got to be consistent, like which one are you subtracting from which? And let's say this calculation's Amazon minus UCLA. So Amazon minus UCLA difference. So one is minus 4 plus 2 plus 3. And then we can do the same one mean test that we just did before for the running average with just the difference variable, one single variable. Once again, what do we ask first? Normality and independence. Is the data normal and independent? So in their sample that we did here, I had some examples here. What do you think? Does this look normal? Well, based on the book standards, this is pretty normal. You can we do have some extreme values, but seems kind of normal, so we'll let it pass. And then, well, is it independent? Yes, we did. We used kind of took a random sample of the books, and it was pretty standard random sample. So we know it's independent, and then kind of looks normal, so we're gonna assume it's okay. And then we can see, oh, here they already took the difference, so we're already using the difference as the variable. So the average, or the most price is around zero, the difference between the two. And here, note that it's UCLA minus Amazon, and the way I just wrote before is Amazon minus UCLA. That will make a difference. The total is going to invert your values. So you need to know which one is which. You have to be consistent. So I just did it here, kind of just to point it out to you, but it's definitely very important you know which one you're subtracting from which, because you only have two and you don't want to know which one is cheaper, which one's more expensive. So if you just confuse one, you get your whole answer completely wrong. So you do want to know which one you're subtracting. In the textbook example, it's UCLA minus Amazon price. So the mean is around zero, because it's pretty close. Like some books are just a little bit close, $1 difference or negative $1 difference. And then, but some books are more like $20 differences and so on. So notice how this is already the difference, and that's the only variable we need to use. And then, so the hypothesis test is we're going to assume that the difference equals zero, and that as the null hypothesis, well, we should assume that they're the same. That's our null expectations, or So the true mean difference in the new textbook prices is equal to 0. And then, but we're going to set up a hypothesis that no, actually that we are kind of, our hunch is that the difference is above 0. So if you're subtracting UCLA minus Amazon, then that means that the UCLA are more expensive. You're testing that this UCLA is more expensive. Now, you could have just set up as different than 0, in which case you would need to use the two-sided test. Because we just said greater than 0, we can just look on one side of the distribution. But I don't know. I think we should have just, yeah, I guess the data suggests that it's C. All these more books are higher. And, once again, we CLA minus Amazon. So if we have positive numbers, that means UCLA is more expensive. So there is a hint that the UCLA is more expensive. So you can either take either approach, greater than or equal or just different than 0. Check the independence. Yes, we did that. While there's some outliers, none of the outliers are particularly extreme. Yeah, okay, we can move forward with the t-distribution. So the first step is set up the hypothesis and check the normalities. This is 0, right? The first ground 0 before we even begin. Okay, then our step 2 was compute the standard error of the difference. But once again, we're just focused on the difference now. We're not focusing on the Amazon price nor the UCLA price, but the difference. As divided by the square root of n, we got the number 163. This is the standard error, kind of like standard deviation, but in the terms of the variable that we're measuring the difference, but not exactly. The more like standard deviation is the t-score itself. So we use the standard error to help calculate the t-score, which is going to be our mean of the data minus 0 divided by the standard error. So the mean of our actual data of the difference between UCLA minus Amazon is 3.58. So it's greater than 0. Minus 0 divided by 163 is 220. So what is 220? Well, 220, once again, is the t-score. That means this value is 2.220 standard deviations, which is over here. So that's 2.220 standard deviations. It's also depending on, so the difference here, we are measuring in the terms of the price. Here, we're measuring in terms of standard deviations. 2.2 standard deviations. So what do we do to find the p-value? Now we need the p-value. See that this value tells us that the sample mean difference in price 3.58 is 2.2 standard errors. Sorry, standard errors, we should say standard errors above 0. And it's 3.58. So now we need to input this t-score into that PT function as we did before. So we had the PT function and we'll put the 2.2 comma degrees of freedom, df equals, what's the degrees of freedom? Sample size 68, so degrees of freedom is 67. And then what's the value we get? Well, the value we get is, remember, so because we're using plus, because we're using a positive t-score, we're going to need to do 1 minus the result from this. And that is, it's going to give us 0.0156. So it's really 1 minus 0.99. Some kind of 0.98, 4, something like that. So if we don't do a 1 minus, this function, this PT function, is going to give us 0.9844. So that's not the p-value we really want because of what we explained before, the way that the PT function counts. So we want to know this area under the curve here. If we just print out whatever the PT gives, we're going to give this area under the curve here. And we don't know, we want to know how likely it is to get this extreme value or more extreme. And the chance is 0.0156. So here would have been 0.9844. So we got to subtract from 1 and you give 0.0156. So the area under the curve here is 1.56%. So that's a 1.56% chance. Is that statistically significant? Yes, because as long as we want the p value to be less than 0.05. So the p value is less than 0.05. We say that it's statistically significant. So this difference is very high. It's very far off from the mean. Then we can expect that the alternative hypothesis is true, and we can reject the null hypothesis and suggest that yes, the difference is greater than 0. UCLA prices, we can be confident that UCLA prices are greater than Amazon prices. And we can also calculate the confidence interval once again, as we did before. And that's a wrap for this one. Oh yeah, there we go. We calculated over here. Create a 95 confidence interval for this average price difference. We just got to plug in the formula, but first we need to use that QT function to find out where that T asterisk is for that 95% confidence level. And I know it seems a little bit weird, like 95% confidence, why we put 97.5 here. It's because 95% confidence is within the area, because now we're finding the confidence interval of the mean, of the central point. So it's from the center. And we got 2.5 here and then 2.5 here. So the QT, if you put 0.975, which is 1 minus 0.025, you get 2. So 2 here. We don't need to do it to the other side, as I mentioned before, that you can assume that it's negative 2 and 2. So we have our average price. This is X bar, the sample mean, the sample of the difference. 3.58 plus or minus 2. That's the T, our T score, T cutoff, times 163, which is the standard error that we calculated before. And then we get this confidence interval that we can be 95% confident that the difference between the prices between UCLA and Amazon books are between 0.32 cents and $6.85. And that's what all this means. And then here I have just a summary of the steps. So to wrap it up, check normality and dependence conditions of the sample. Sometimes you have to know what the random sampling process was. Not sometimes, always you need to know what the random sampling process was. And if there was there and if it was valid, then it's good. And then you can check the normality based other knowledge about the domain and the statistics, the sample statistics itself. We calculate the mean, standard deviation, minimum, maximum values as usually in degrees of freedom, because we're going to use that in our equations. You set up your null and alternative hypotheses as your confidence and your confidence level for your confidence interval, and for your p-value. They're different. There's confidence level for p-value, and there's one for the confidence interval. They're usually both 95% confidence interval. So, but they're not the same. They use them in different ways for different calculations. Then you calculate the t-score and use that measure with the degrees of freedom to find the p-value of the t-score. And for the t-score, you're going to need to calculate the standard error of your sample. And then you plug that into the PT function. You put the t-score in with the degrees of freedom. And then that gives you the likelihood of you getting that t-score value. Now, just remember that if your t-score is positive, you need to subtract it from 1. And if you're doing a two-sided test, you don't know if it's greater or less, you need to then also multiply it by 2. Okay. Uh, let's improve this here. So if you have a positive t-score, you do 1 minus. And if you have a negative t-score, you don't need it. So that's the idea. And then calculate the confidence interval given your t cutoff, confidence level, mean, and standard deviation. So for the t cutoff and the confidence level of the confidence interval, you need to put into the qt function, and usually 0.975, or the other side you can also put 0.25, 0.025 with the degrees of freedom, and then maybe you get like something like 2, and then you can assume it's 2 and minus 2 for both sides because it's symmetric. So those are the steps to do both test your statistic and find a confidence interval for the one mean value and also the difference of values of two variables. I hope this was useful, and I'll see you next time.